Assalamu alaikum. In this video, we'll get the relation between focal length and radius of curvature of a given spherical mirror. For this, I considered a concave mirror. Let's consider this one as a concave mirror. Every mirror has got two sides. A surface which do not reflect light is called as the non-reflecting surface of a mirror. Currently speaking, this side of the mirror is a silvered, okay, and the opposite side, the second side of the mirror is called as the reflecting surface. Here I take the center of this mirror. We call the geometric center of a mirror as a pole, okay, and the line which passes through this pole is referred as principal axis. So this is the principal axis, and here this center, geometric center of this mirror is called as pole. Okay, now I'll take a ray, a parallel ray, a ray which goes parallel to the principal axis. So this is the incident ray. It incident on the concave mirror at point M. Now we know very well a mirror in which the reflecting surface is curved in is referred as a concave mirror. Now the center of the sphere of which the spherical mirror is a part is referred as the center of curvature. I take this one as the center of curvature. Point C is taken as the center of curvature of this spherical mirror. Now when this parallel ray reflects, it incident at one point on the principal axis. We call this point as F, which is nothing but focus. Sometimes it is also referred as principal focus. This is the reflected ray. Now, the line which connects the center of curvature and the mirror is known as the normal. This is the normal line that passes through the center of curvature and meets the mirror. It is referred as the normal. With respect to normal, we measure all sort of angle. The angle between the incident ray and the normal is called as angle of reflection. Sorry, angle of incidence, represents letter I. And here, the angle between reflected ray and normal is nothing but angle of reflection. Here, according to law of reflection, angle of incidence equals to angle of reflection. So I is equal to R. By keeping this in mind, here R is replaced with the I. Okay. So the total angle between incident ray and the reflected ray is 2I. By following geometrical rules, if this angle is 2I, then this angle will be nothing but 2I. So similar way, if the angle between the incident ray and the normal is I, means the angle between the principal axis and the normal is also I. Okay. If you look at this diagram carefully, you may find that it is supposed to be forming two right angle triangles. To make my work more easy, for better understanding, I drop a perpendicular from here, which meets at a point very close to the pole. Now it won't be wrong if I take this point as a P. Okay, it is very close to the pole of the given mirror. Am I right? Now it is obvious that it forms two right angle triangle. This one right angle triangle MCP. Another right angle triangle is nothing but MFP. So we have two right angle triangle. The first I'll take a right angle triangle MCP. So here tan of angle I is found to be opposite side divided by adjacent side. So what is the opposite here? Opposite to the angle is nothing but MP, and the adjacent side is CP. I take this as equation number 1. Then I'll go ahead. I'm going to find out the tan of angle 2i from right angle triangle MFP. Right angle triangle MFP. Take a tan of 2i, which is obtained by following the same formula, opposite divided by adjacent side. So what is the opposite side? MP divided by FP. I take this as equation number 2. Now from the diagram it is obvious that angle I and 2i, angles I and 2i are very small. So for this reason, we know if the angle is very small, then tan theta can be written as a theta. Similar way, tan I is written as I, and tan 2i can be written as a tan 2i can be written as 2i. Now I am going to use these things in equation number 1 and 2. So equations 1 and 2. Take a new form. What is that? Here, instead of a tan I, I write I, which is equal to MP upon CP. This is equation number 3, and 2i is taken as MP upon FP. Here tan 2i is written as 2i, which is nothing but MP upon FP. This is taken as equation number 4. Okay. Now I am going to use equation number 3 in 4. Using 3 in 4. What I am going to do? So I take a 2. In the place of I, I'll write its value. That is MP upon CP equals to MP upon FP. Here MP and MP get cancelled, and what we get is nothing but this 2 1 upon CP equals to 1 upon FP. This is equation number 5. It is taken as equation number 5. Understand? Now from the diagram, if you look at the diagram carefully, you may find that here the distance between pole and the focus, this distance is taken as small f, that is the focal length of the given spherical mirror, and the distance between pole of the same mirror and the center of curvature is nothing but radius of curvature. It is taken as capital R. So by keeping this in mind, here FP is nothing but small f and CP is nothing but capital R. I am going to use these things here in this equation number 5. So equation number 5 takes a new form. So 2, in the place of CP I write R, capital R. In the place of FP I write small f. Now I am going to cross multiply this. F is taken that side. It is in denominator, and it is taken to the another side, it will multiply. It will go to numerator. So it will become 2f. And R, which is in denominator, when taken to the another side, it will move to numerator. So we get a new relation, according to which 2f equals to R. This can be written as f equals to R upon 2. So this clearly shows that focal length of a given spherical mirror is half of the radius of curvature of that spherical mirror. Clear? This is a relation. I represent this by letter by equation number 6. Understand? And the same thing holds good for convex mirror as well. Now, suppose if you want to find the relation between F and R for a convex mirror, then how the diagram will appear? Let me show this to you. In case of a convex mirror, the reflecting surface is merged on. This is the reflecting surface. This one is the non-reflecting surface. And here, this is taken as the center. The center of a given spherical mirror is nothing but the pole. Okay, and the line which passes through the pole is called as principal axis. This is the principal axis. Now, just extend this. This is the center of curvature for the given spherical mirror, represent letter C. Now, suppose I take a ray, a parallel ray with incident at this point. I take this point as M. Then it gets reflected from there. Okay. Suppose maybe in this direction. This is the incident ray and this is the reflected ray. If you just continue this, you find that it incident at some point. This is F. So this center of curvature brought forward here. Will fall somewhere here. We will try this diagram. I have rectified this diagram earlier. By mistake, I marked the center of curvature here, but actually it falls somewhere there. Now, the line which connects the center of curvature and the mirror is taken as the normal. Okay, this is the normal, and here this angle between the incident reflected ray and the normal is taken as R, no, which is equal to I. So here the angle between incident ray and the normal is taken as I. Okay, here I is equal to R, so this angle can be taken as I. So the total angle is 2I. If it is so, here, before I go ahead, I'm going to drop a normal here which meets at a point which is very close to the pole. So I take this point as pole. Now if you look at this carefully, you may find that it has formed two right angle triangle. If this angle is 2I, then this will be 2I, because we have just extended this line which meets at point F. Okay, and a second thing, the angle between these two is going to be I, because it is the extension of the normal. The normal makes an angle of I with the incident ray, means the angle between normal and the principal axis, which is just parallel to incident ray, is going to be I only. Okay. So by using this diagram, one can get the relation between F and capital R for a given convex mirror. I hope the video is useful. If you have any kind of doubt relevant to the topic, kindly put your question in the comment section. Thanks for watching.